Good morning, or whatever it is there. Hey, strange people that watch my channel. So, I had this thought earlier today, and it seemed like an insane epiphany. Of course, in retrospect, a little bit, it's like, oh, duh, that's sort of obvious or something. And I think it's basically all about this Ricci curve and how the energy impinges on space-time to curve it. And my whole thing that space is essentially thesiotropic, so that and the shear stress is energy. As you put energy into space, space gets more dense, but also becomes less viscous. And I think basically that attribute, that collection of attributes for space, explains all of the behavior that we look for, and in quantum mechanics and everything, if we use that as a fluid model. We'll get to that. Today's epiphany was simply that fundamentally, distance is inversely proportional to energy. Okay? Because when you're in space, deep space, there's very low energy, and we're going to include mass in energy because mass is made out of energy. We'll get to that later too, probably. Okay, but fundamentally, distance is inversely proportional to energy. And this is because space behaves as if it was sort of like a density of somethingness. Very Maxwellian, I know, okay? And we can solve for all of this. So look at, you have let's just imagine that distance is energy. So this is energy density. This is deep space where there's like, let's imagine a proton, proton, proton. These are the electron fields around, so they're huge. There's 1 proton per meter. So this is 1 cubic meter, let's say. Okay. Ooh. And then here we have that same hydrogen, only like, let's say this is atmospheric, Earth atmospheric density. Okay. So a photon will pass our distance, and the way we measure distance is, let's just say 3, 1, or 2. Ooh. Okay, 2 sine waves, basically. Okay, so that's 1, 2. Okay, and here we get the same distance in a way. It's the same energy distance. Because the energy density is higher, you only get to move a certain number of Plancks with your energy. When the energy density is higher, you can't move as far. This is the slow time thing. It's like eventually, this is so dense, that's molasses, you can't move, so it's as if there's only one moment that you're ever going to have. Whereas here, there's nothing, there's an unfettered passage. That all gravitational lensing is essentially like this, where it's like, and then all of a sudden you hit some slow medium, it's like you're traveling through space and you hit some water, only it's weird amorphous water because it doesn't have a boundary in the same way. But this distance is inversely proportional to energy density. Okay, and just because I'm annoying, and I'm going to iterate this until somehow it gets through to the universe, that mass. Okay, mass is like that. Why is mass mass? Because it's contained in a rotation. It's energy contained in a rotation. Therefore, there's only this much distance for an unlimited amount of energy, because it's never going to go further than that. It's trapped in orbit. Okay, mass is equal to E over c squared. Okay. Mass is energy in orbit acquiring this angular momentum. I don't even know the symbol for angular momentum, but that's what you get. You get the angular momentum. This is only one Planck. This is moving at c. Boop. You end up getting a proper 2 pi Planck frequency photon in orbit over itself, which creates an energy density such that the Schwartzchild radius is still 2 pi Planck. So you're basically a bunch of energy sitting in orbit, getting angular momentum, becoming mass. These are the two charge things left over when you do a proton and a neutron. Okay. Up, up, down, up. Two charges. Up. One, oh, two charges. Second up. Third charge. Ooh, gosh, we got an extra charge. Let's throw that in the middle. The down. Oh, perfect. This mass. Let's do the neutron. Really, I can't believe this ever takes so much. Yeah, down, down, up, down, down, up. Basically brings all of that together. Now you have mass. Only you've got two masses sitting on the same space there. Okay, you've got two masses sitting on top of each other. I think that's the problem with the neutron. It's basically it becomes one of sharing the surface. Okay, when you're a proton, you have this is your mass sphere, which possesses every single possible at any given time. Let's say make it like an egg. At any given time, this is highest energy, this is lowest energy. Every possible energetic state is being expressed on this single thing at any given moment. It's like noise in a way, only it probably has an oscillation, but it's oscillating in light, so we're going to have a hard time measuring light over a Planck. Anyway, so, but all possible states of energy level are trapped around this Planck, right? In a proton, and then you have some charge around it, and that creates a reciprocal charge, the electron field, which I say is it just actually a mirror of the charge of the proton itself. Yes, so, but when you have in a neutron, you've got two of these mass photon units on top of each other. Okay, and therefore they start to bump into each other. There's a chance of their bumping. In fact, there might be one of those statistical pole things where there has to be 2 points at any given moment where they are interfering with each other automatically. You know, just like there's going to be a highest and lowest point in this sort of thing. Okay, so this is where mass comes from. Those charge units left over from your quark math stuff. With a frequency of 2 pi Planck, and distance is inversely proportional to energy density. And I think this is actually particularly pertinent to Stephen Wolfram's project. Stephen, the energy density, as I mentioned in comments, but probably they get lost because I'm in that, what can I say? That, yeah, the more people, the more paths that are using one of your vertices, right? The more paths that are using a single vertex, that basically is energy density along that one path. That should be shortened proportionally to give you the proper geometry that would represent the kinds of energy densities we're talking about. Okay, so I think maybe this is just nuttiness, but it was a weird epiphany I had. Distance is inversely proportional to energy density, because when there's low energy density, you can get very far, and when there's high energy density, you can't get as far. Distance is shorter, distance is longer, because this is true distance. See, we cheat when we imagine laser beam going through the piece of plastic, like there's a line going from that room to that room, and I put this in between, you say, oh yeah, but that line's still there. And that's because we're using this imaginary path of least energy. That's exactly it. The path of least energy is this one. Okay, this is the path photons use. This is the entanglement path. It's like when you have billiards all in a chain, they're all touching each other. When you hit one, immediately, like the energy transfer is faster than going around these, which is what a photon does. Positive part, negative part, positive part, negative part. Even though a single photon is only one ripple. It drives me batty that people put chains as if it's a laser always, but a photon is a singular object. There. Okay, I'm gonna end this in 11 minutes. Okay, have a beautiful day, everybody.